In the previous video, we have discussed the behavior of two interconnected mismatched solar cells. Now, we will see how to prevent the power loss caused by the mismatch by using bypass and blocking diodes. In particular, we shall look at the case in which the mismatch is caused by shading, and thus the lifetime of your PV module is threatened by hotspot heating of the cell. To avoid junction breakdown, we use bypass and blocking diodes, which are necessary in real-life conditions. Let's first see what happens when the solar cell is full or partially shaded. If the cell is not covered, then the typical IV characteristic is reported in the graph. But things change as the coverage increases, and thus a partially shaded cell shows a rigid shift downwards of the current voltage characteristic. The shaded region is directly proportional to the shift until the cell is fully shaded, and thus the photocurrent generated is null. Problems arise at module level because the shading of a single cell implies a current mismatch in the PV module. So it is important to know what is the topology and how the cells are connected together. For example, depending on how you mount the module, vertically or horizontally, and its internal configuration, your module can be more or less resilient against the shading. A module made up of series connected solar cells would have zero output power even if only one cell is completely shaded. But the situation is different when the module is made of two branches connected in parallel. Indeed, it can happen that only one branch is shaded, so at least the other one can deliver some power. An example of a hotspot heating may occur when one out of 10 series connected cells is completely shaded, causing the good cells to counterpolarize the shaded one. As a consequence, the occurring power dissipation is concentrated on the small area of the shaded cell, and it causes a local overheating or hotspot. And hotspot may lead to destructive effects such as cell or glass cracking, as shown in the picture, or even melting of solder materials and the degradation of the solar cell, dramatically decreasing the module lifetime. As we have already seen, a solar cell inside the circuit is represented with a current generator and a diode in parallel. The corresponding IV curve is depicted in the graph on the right-hand side. Now we are going to introduce you an additional element called the bypass diode. Its role is to avoid the destructive effect of hotspot heating when a solar cell is dissipating power of other cells in case of current mismatch. Therefore, the role of a bypass diode is to preserve module integrity and lifetime. Such a diode is connected in parallel but with opposite polarity with respect to the cell. This means that in normal operation, each solar cell is forward biased, while the bypass diode is reverse biased. In the graph, it is reported how the current voltage characteristic changes when introducing the bypass diode. Between 0.6 and 0.7 volt in a negative bias, the bypass diode is activated, and it will raise immediately the current, avoiding the breakdown of the cell. Let's now place two solar cells in series and investigate their behavior more in detail. In case of open circuit, whatever is the illumination condition on each cell, the two devices will not be connected to any load, and we would just see the sum of the two voltages. When we short circuit the two solar cells and we are in a current matching situation, then both cells are delivering the same amount of current as depicted by the red arrows, and the bypass diodes are inactive, being reverse biased. The positive effect of the bypass diode kicks in when there is a current mismatch. Here, the green cell receives more irradiance and has a forward bias. On the other hand, the partially shaded blue cell is reverse biased. In these conditions, the bypass diode is thus activated. Indeed, the current that was supposed to flow through the shaded cell would instead activate as soon as possible the bypass diode that is mounted counterpolarized with respect to the cell. This means that when we have two cells in series that are short-circuited, then the cell receiving lower irradiance would see a negative bias, which would activate the bypass diode that is mounted counterpolarized. So all the excess current that would eventually flow inside the cell actually flows within the bypass diode, preventing the cell to have a large amount of power being dissipated in it. Let's come back to the example shown at the beginning of the lecture, and let's draw the IV characteristic of the string when cells are equally illuminated. In case one cell is completely shaded and there is no bypass diode, then the total current voltage characteristic just drops down with a total voltage that is more or less the same, but then the maximum current is dictated by the partially shaded cell. In order to prevent that all the excess current would be dissipated in it, we must use bypass diodes. Considering now the performance of the whole string, we have that the total current voltage characteristic has two knee values, which correspond to two local maxima of the power. Still, some power is dissipated in the shaded cell, but it is much less than the case without a bypass diode. In addition, a bypass diode is designed and fabricated to withstand also important thermal budget. All in all, the use of bypass diodes ensures a good yield also in partial shading conditions and saves the lifetime of your module. In practice, however, it is not viable to use one bypass diode per cell because this solution would be too expensive. Usually, bypass diodes are placed across groups of solar cells depending on the breakdown voltage of the single cell. The maximum power dissipation in this shaded cell is approximately equal to the generating capability of all cells in the group, and thus for silicon cells, the maximum group sides per diode without causing damage is about 15 cells per bypass diode, which means that for a normal 36 cells module, 2 bypass diodes are needed to ensure that the module will not be vulnerable to hotspot damage. Until now, we have seen series and parallel connection among cells within the module, but note that you can also have modules that are connected together in strings and then in arrays. So we have to project the same type of problems discussed at cell level to module level. Let's imagine a very large PV plant of hundreds of modules. It may happen that one part of the plant is partially shaded by clouds, while the other is still well illuminated. As a consequence, partial shading without bypass diodes generates a very huge imbalance that even for a few seconds can hinder the lifespan of the complete PV system. The last topic of this video is the blocking diode. It is used in parallel connected strings or modules in order to prevent current flowing from one parallel string into a lower current string due to partial shading. Therefore, each string to be connected in parallel should have its own blocking diode. Moreover, in systems with batteries, blocking diodes are typically employed to prevent the module from loading the battery at night by preventing current flow from a battery through the PV array. To conclude this video, we have introduced two important components, the bypass diode and the blocking diode, that prevent the negative effects of current mismatch caused by partial shading. In the next video, we will see instead the effects of temperature and irradiance on the performance of the module.